Overload relays typically rely on thermal elements that detect excessive heat buildup over time. They are designed to protect against overload conditions, but may not open quickly enough in locked rotor situations where high inrush currents are present. Motor protection relays offer advanced features that allow for rapid detection and protection against locked rotor conditions. They use current sensors and algorithms to identify locked rotor events and trip within a specific time delay. Circuit breakers equipped with electronic trip units can provide both overload and short-circuit protection. They offer adjustable time current curves that can be set to detect locked rotor conditions and trip accordingly. Current sensors can monitor motor currents and send signals to a programmable logic controller (PLC). The PLC can be programmed to detect locked rotor events and initiate protective actions, such as opening a contactor or tripping a circuit breaker. Some motor starters incorporate both overload and locked rotor protection devices. These devices can provide fast and effective protection against both conditions. The choice of protection device depends on the specific application, motor characteristics, and desired protection level. Proper sizing and setting of protection devices are crucial to ensure effective protection without nuisance stripping. Regular maintenance and testing of protection devices is essential to ensure their reliability. When dealing with motor protection, it's important to understand the differences between overload protection and short-circuit protection. Overload protection, typically provided by overload relays, is designed to protect the motor from overheating due to prolonged overcurrent conditions such as a mechanical overload. These devices operate on the principle of thermal buildup, meaning they respond to the heat generated by excessive current flowing through the motor windings over time. They are intended to allow temporary overloads, such as those experienced during motor starting, but will trip if the overcurrent persists for too long. Short-circuit protection, on the other hand, is designed to quickly interrupt very high currents that result from a fault in the electrical system, such as a short circuit to ground or a phase-to-phase fault. Fuses and circuit breakers provide this type of protection, and they operate almost instantaneously to prevent damage to equipment and wiring. The National Electrical Code, NEC, specifically addresses motor protection requirements in Article 430. This article provides detailed guidelines on sizing overload protection, short-circuit protection, and conductor sizing for motor circuits. It also covers various types of motor controllers and protection devices, as well as their application and installation. A locked rotor condition occurs when a motor is unable to start or rotate due to a mechanical obstruction or electrical fault. In this situation, the motor draws a very high current, known as the locked rotor current, which can be several times the motor's full load current. If this condition persists for too long, the motor windings can overheat and be damaged. Standard overload relays may not respond quickly enough to a locked rotor condition because they are designed to protect against gradual overloads, not sudden high currents. This is where motor protection relays come into play. Motor protection relays are specifically designed to detect and respond to locked rotor conditions. They use current sensors to monitor the motor current and algorithms to identify the characteristic current signature of a locked rotor event. When a locked rotor condition is detected, the relay will trip the motor starter, disconnecting the motor from the power supply and preventing damage. There are several types of motor protection relays available, each with its own set of features and capabilities. Some relays offer adjustable trip settings, allowing you to customize the protection to match the specific motor and application. Others provide advanced features such as undercurrent protection, overvoltage protection, and phase imbalance protection. In addition to motor protection relays, circuit breakers with electronic trip units can also provide effective locked rotor protection. These circuit breakers have adjustable time current curves that allow you to set the breaker to trip quickly in response to a high current, such as a locked rotor current. The time current curve defines the relationship between the amount of current flowing through the breaker and the time it takes for the breaker to trip. By carefully selecting the appropriate time current curve, you can ensure that the breaker will trip quickly enough to protect the motor from damage, while also avoiding nuisance tripping during normal motor starting. Another approach to locked rotor protection involves using current sensors and a programmable logic controller (PLC). The current sensors monitor the motor current and send signals to the PLC. The PLC is programmed to analyze the current signals and detect locked rotor conditions. When a locked rotor condition is detected, the PLC can initiate protective actions, such as opening a contactor or tripping a circuit breaker. This approach offers a high degree of flexibility and customization, allowing you to tailor the protection to meet the specific needs of your application. Some motor starters incorporate both overload and locked rotor protection devices into a single unit. These devices offer a convenient and cost-effective solution for protecting motors from both overload and locked rotor conditions. They typically include an overload relay for overload protection and a current sensing device for locked rotor protection. When selecting a motor starter with locked rotor protection, it is important to ensure that the device is properly sized for the motor and application. The device should be able to handle the motor's full load current and locked rotor current, and it should have appropriate trip settings for the specific application. Regardless of the type of protection device you choose, it is essential to ensure that it is properly sized and set up. Improperly sized or set up protection devices can lead to nuisance tripping or, worse, failure to protect the motor from damage. The NEC provides detailed guidelines on sizing overload protection and short circuit protection for motor circuits. These guidelines should be followed carefully to ensure that the motor is adequately protected. In addition to proper sizing and setup, regular maintenance and testing of protection devices is essential to ensure their reliability. Overload relays and circuit breakers should be inspected periodically to check for signs of damage or wear. They should also be tested to verify that they are operating correctly. Motor protection relays should be tested regularly to ensure that they are accurately detecting and responding to locked rotor conditions. Testing can be performed using a motor protection relay test set, which simulates various fault conditions and allows you to verify the relay's performance. When selecting protection devices for motor circuits, it is important to consider the specific application, motor characteristics, and desired protection level. Some applications may require more sophisticated protection than others. For example, a critical motor that is essential to the operation of a plant may require more comprehensive protection than a less critical motor. The motor's characteristics, such as its full load current, locked rotor current, and service factor, should also be considered when selecting protection devices. The desired protection level should be based on a risk assessment that considers the potential consequences of motor failure. In addition to the NEC, other standards and guidelines can provide valuable information on motor protection. IEEE Standard 242.2001, the Guide for Protection and Coordination of Industrial and Commercial Power Systems, offers comprehensive guidance on the protection of electrical systems, including motor circuits. UL Standard 508A, the standard for industrial control equipment, provides requirements for the design, construction, and testing of industrial control panels, including motor starters and protection devices. When working with motor circuits, it is important to follow all applicable safety precautions. Always energize the circuit before working on any electrical equipment. Wear appropriate personal protective equipment, such as safety glasses and gloves. Follow lockout-tagout procedures to prevent accidental energization of the circuit. If you are not qualified to work on electrical equipment, consult a licensed electrician. In summary, there are several ways to detect and protect against locked rotor conditions in motors. Motor protection relays, circuit breakers with electronic trip units, and current sensors with PLC can all provide effective locked rotor protection. The choice of protection device depends on the specific application, motor characteristics, and desired protection level. Proper sizing and setting of protection devices are crucial to ensure effective protection without nuisance tripping. Regular maintenance and testing of protection devices is essential to ensure their reliability. By following these guidelines, you can protect your motors from damage and minimize downtime. Firstly, it is important to understand the fundamental differences between overload relays and fuses in the context of motor protection. Overload relays, typically thermal overload relays, are designed to protect a motor from sustained overcurrent conditions that could lead to overheating and damage. These relays operate on the principle of thermal accumulation, meaning they respond to the heat generated by the motor's windings due to excessive current flow over time. They are designed to allow short-duration overcurrents, such as those experienced during motor starting, but will trip if the overcurrent persists beyond a specific time current curve. Fuses, on the other hand, are primarily designed for short circuit and ground fault protection. They are intended to quickly interrupt very high currents resulting from a fault in the electrical system, such as a short circuit to ground or a phase-to-phase fault. Fuses operate almost instantaneously to clear these faults, preventing catastrophic damage to equipment and wiring. Fuses are not typically intended for overload protection, although they can provide some degree of overload protection depending on their characteristics and the magnitude of the overcurrent. Secondly, in the specific scenario described, the 20 amp general use receptacles are protected by 20 amp Bussmann LPCC20 fuses. The motor in question is a 7.5 horsepower, 480 volts, 9.6 amp 3-phase motor. The overload relays are set at 9.6 amps, which corresponds to the motor's full load amperage flaw. According to Table 430.52 of the National Electrical Code, NEC, the maximum fuse size for a Class CC fuse used for motor branch circuit protection can be up to 300% of the motor's FLA. In this case, 300% of 9.6 amps is 28.8 amps. However, the existing fuses are rated at 20 amps, which is less than the maximum allowable size. The locked rotor current, LRC, for the motor can be estimated using Table 430.151b of the NEC. Assuming a design code E motor, the LRC is approximately 91.5 amps. This is significantly higher than the fuse rating and the overload relay setting. Thirdly, the problem arises because the locked rotor current is high enough to blow the 20 amp fuses before the overload relays can trip. The overload relays are designed to protect against sustained overcurrents, but they may not respond quickly enough to the very high current associated with a locked rotor condition. The fuses, being designed for short-circuit protection, are likely to blow before the overload relays can trip, resulting in nuisance fuse replacements. Fourthly, there are several ways to address this issue. One option is to upgrade the overload relays to motor protection relays with locked rotor protection. These relays are specifically designed to detect and respond to locked rotor conditions, and they can trip much faster than standard overload relays. Motor protection relays typically use current sensors and sophisticated algorithms to identify locked rotor events and initiate a trip signal. Another option is to use circuit breakers with electronic trip units instead of fuses. Circuit breakers with electronic trip units offer adjustable time current curves, allowing you to set the breaker to trip quickly in response to a high current, such as a locked rotor current. The time current curve defines the relationship between the amount of current flowing through the breaker and the time it takes for the breaker to trip. By carefully selecting the appropriate time current curve, you can ensure that the breaker will trip quickly enough to protect the motor from damage, while also avoiding nuisance tripping during normal motor starting. A third option is to use current sensors and the programmable logic controller, PLC, to detect locked rotor conditions. The current sensors monitor the motor current and send signals to the PLC. The PLC is programmed to analyze the current signals and detect locked rotor conditions. When a locked rotor condition is detected, the PLC can initiate protective actions, such as opening a contactor or tripping a circuit breaker. This approach offers a high degree of flexibility and customization, allowing you to tailor the protection to meet the specific needs of your application. Fifthly, it is important to consider the coordination between the overload protection, the short-circuit protection, and the motor's thermal withstand capability. The overload protection should be sized to protect the motor from sustained overcurrents, while the short-circuit protection should be sized to protect the wiring and equipment from short circuits and ground faults. The motor's thermal withstand capability is the amount of time it can withstand a specific overcurrent without being damaged. The protection devices should be coordinated such that they trip before the motor's thermal withstand capability is exceeded. In this case, the 20 amp fuses are likely providing adequate short-circuit protection, but they are blowing too quickly in response to locked rotor currents. Upgrading the overload relays to motor protection relays or using circuit breakers with electronic trip units can improve the coordination between the overload protection and the short circuit protection, allowing the motor to be protected from both overloads and short circuits without nuisance tripping. Sixthly, it is important to address the misconception that overload relays respond to voltage spikes. Overload relays are designed to respond to overcurrents, not voltage spikes. They operate on the principle of thermal accumulation, meaning they respond to the heat generated by the motor's windings due to excessive current flow over time. Voltage spikes can damage electronic equipment, but they do not directly cause overload relays to trip. If voltage spikes are a concern, surge protection devices, SPDs, should be installed to protect the equipment. Seventhly, the switch from 20 amp fuses to 20 amp circuit breakers is not necessarily a solution to the problem. While circuit breakers can be more convenient than fuses, they may not necessarily provide better protection against locked rotor conditions. The circuit breaker must have an appropriate time current curve to trip quickly enough in response to a locked rotor current. If the circuit breaker's time current curve is not properly selected, it may not trip any faster than the fuses, and the problem will persist. Eighthly, here is a summary of the key considerations for addressing the locked rotor issue. Evaluate the existing overload protection and determine if it is adequate for protecting against locked rotor conditions. Consider upgrading to motor protection relays with locked rotor protection or using circuit breakers with electronic trip units. Ensure that the protection devices are properly sized and set up according to the NEC and other applicable standards. Coordinate the overload protection, the short circuit protection, and the motor's thermal withstand capability. Install surge protection devices, SPDs, if voltage spikes are a concern. Educate personnel on the proper operation and maintenance of motor protection devices. Ninthly, consult the following resources for further information on motor protection. National Electrical Code, NEC Article 430, Motors, Motor Circuits, and Controllers. IEEE Standard 242.2001, Guide for Protection and Coordination of Industrial and Commercial Power Systems. UL Standard 508A, Standard for Industrial Control Equipment. Busman Fuse Selection Guide. Allen Bradley Motor Protection Relays Catalog. Tenthly, in the specific scenario described, the most effective solution is likely to upgrade the overload relays to motor protection relays with locked rotor protection. This will provide faster and more reliable protection against locked rotor conditions, reducing the number of blown fuse replacements and protecting the motor from damage. The motor protection relay should be properly sized and set up according to the motor's characteristics and the application requirements.